Okay, so maybe we can just get started. So first, it's an honor to introduce Professor Sami Khan. So Sami received his PhD in 2007 from the University of Texas, and currently he is department head and the James Bagley Chair in Electrical and Computer Engineering at Mississippi State University. So before arriving at MSU, he was a cluster lead for the computer systems research at the National Science Foundation and the Walter B. Booth Professor at North Dakota State University. So his research interests include optimization, robustness, and security of computer systems. He has published over 400 papers and is an associate editor-in-chief of IT Professional and an associate editor of IEEE Transactions on Cloud Computing, the Journal of Parallel Distributed Computing, and ACM Computing Surveys. But most interestingly, I think Sami has been very active in terms of our community. He is also an ACM distinguished lecturer and IEEE distinguished lecturer. So it's a true honor to have him. And he's also contributed to our community through the DSCS, which is the IEEE Scalable Computing Initiative. So I look forward to listening to Sami's talk. And again, please ask question and answers using the tab at the bottom. Sami, over to you.
Well, thank you so much, Omar. It's truly the honor belongs to me, and I really appreciate you extending the invitation. At this particular instance of time, I'm really envious for everybody who is in the UK. At least they're getting their shots. we don't know when we're going to get our shots. But anyway, I thought, because this was a kind of a joint talk between two main conferences, I thought maybe bridging the gap would be an interesting idea. I'm not sure how I will succeed, but any instance of time, I want to talk about a topic I'm really interested in. What is the current state of the art? How much do I know about it? How much I should know about it? And what am I looking forward to? And I think these would be the four items or four points that you may want to distill out of it, out of these thoughts. And certainly they are my point of view, certainly not everybody else. Okay. So when I look at IoT, I'm very interested in, why is everybody doing it? Well, the fact of the matter is, yes, everybody is doing it. This is a very nice periodic table that is regularly maintained by CV Insights. I would encourage you to kind of take a look at it. But what do we see over here, right? We have some of the platform enabling companies listed over there, some connected home companies, healthcare, industrial internet, wearable technologies, some connected cars, crowdfunding enabled companies, some are being acquired, and so on and so forth, right? And I look at these companies, except for the very few ones, right, which were the big ones, such as Intel, Verizon, Comcast, the obvious ones that we always think of, right? The majority of these companies are really small, upcoming companies. You wouldn't really tell by looking at their names. You have to really dig into, what are they doing? And that kind of is an interesting fact for me. A lot of stuff is happening in the IoT field, but what is the enabler? What is the bottom line technology, right? I come from a systems community, so I have a different point of view, but going through all of these, interesting concepts emerge, and we'll go through some of them, right? So then, okay, everybody's doing IoT. What is the interesting aspect of it, right? To me, if you look at the entire landscape, right, IoT on its own doesn't really add any value. Big data on its own doesn't add any much of a value. If you look at the edge devices or cloud computing, all of this has to be integrated one way or the other, right? And I think that's where the interesting facts come in. This graph is from Beacon Research in 2017, where they actually, did a cross section of how all of these various technologies interact with each other and what are the, threats that we may face, right? So some of the obvious ones that you can see is because there are different types of, I'm right at the bottom at where the edge devices are. The interfaces have to be redefined or recalibrated simply because, the applications change. Some applications demand a certain type of service. The others do not. Some require access to the hardware, some do not, right? And then, of course, you have to talk to certain types of networks, and this span lengths and breadths of it, right? So you can do from cellular to fixed to satellite to low power LAN. And then some of them are in control systems and in commodity software such as SCADA. These are the power systems, really not really interacting at this particular instance of time with IoT for various different reasons. First of all, I mean, this is a legacy type of a system, right? So to interact with it or to actually tell them this would bring in value would take decades on end. But then, of course, if you have all of these devices, they are capturing data. You need data, right? Fundamentally to figure out what can we do better with our lives, what we can do better with our systems, right? So it does touch the big data paradigm as well. Of course, with all of these cross-sectional type of activities that are happening across the different applications, right? We have new threats emerging. For example, if you look at the healthcare and life sciences, yes, identity theft would be a big element over there. If you just look at the network portions of it, newer elements in denial of service would emerge as well. If you look at the integration in semiconductors and really looking at the hardware elements of it, yes, of course, we have been already exposed to ransomware and maybe some other cyber warfare can be unfolded simply because, we are incorporating all of this hardware from various different sources, and it's very difficult to keep track of, what is being put on them maliciously, or even sometimes it could be an unmalicious type of an activity. Anyway, a nutshell out of this is IoT is important, security is greatly important. Of course, interfacing is a critical element over there. And if you have a huge type of a platform truly being rolled out here, performance also is kind of an issue over there, right? So fundamentally, going back to what I do in practice, optimization, robustness, and security, yes, I can easily plug in. So I was very, very happy about that, right? I can just kind of easily go about it. But then I wanted to know what exactly is IoT, right? So if you open up the literature and the books, wow, there are 11 definitions floating out there, right? And which one is better than the other? I think they're all great. There are a lot of reference architectures available, such as IEEE has its own standards, predominantly looking at the security aspects of it. They do define IoT, and that's really, in my opinion, the definition of a sensor network, and we've dealt with that in the 90s and so on and so forth. So there has to be something new. IETF has reference architectures, quite a bit of it. Again, looking at interoperability and also security. ETSI has recently started to, and this is European Telecommunication Standards, to look into IoT. And again, they're mostly looking at communications, how you can incorporate 5G and so on and so forth. Looking at standardizing NB-IoT and all sorts of these newer technology, which we will revisit in a minute or two. Right? But to me, a clear definition or a meaningful definition that I may subscribe to didn't really emerge until I looked at NIST, right? And they define it as a system that involves 4 things, right? Does involve computation. I think that's a no-brainer right there. Does involve sensing. Does involve communication. But I think the key element there is actuation, right? It's okay to sense things and to compute things on it, to understand it. Of course, this is a distributed system, so by default, you have to have communication there. But if you're not actually acting on it, not closing the loop, then I would really not consider that as an IoT system. That would be simply as a sensing environment, right, or sensing networks, right? So, you can take a look at different types of angles here. You can look at a application-driven interface capability across, the human interaction. Could be just the simple application interface, could be the network interface. And the transducer capabilities would actually be on sensing and also in the actuation. And the support capabilities here would be enabling all sorts of activities related to big data, AI, cybersecurity, and anything else you can think in the middle, right? So that definition to me was very good, because now I can really understand it. Oh yeah, I mean, this makes sense, and it closely resembles to something we already know, which is cyber-physical systems, right? So is it different from the other? Perhaps not. I think what we are looking at more is the scale that an IoT would enable compared to a cyber-physical system, which we will just discuss in a minute or two, right? So what was the interesting fact? Why is everybody interested about it? I think in 2011, there was a study out there which basically laid in my opinion, laid the foundation of, well, it's now called for arms because now we definitely have more connected devices than people, right? And what those devices would mean, well, this is any device that can connect to internet and talk to each other, whether it's a sub-second ping or whether it's a multi-second ping. But that was an interesting fact. What was projected at that time was in 2020, which is actually this year, we would have about 6.58 devices per human, right? And soon we will see that this is way off, but certainly a good starting point. Also wanted to bring you another study in 2014. This is by Cisco, when they asked all of their customers, whoever they were serving, that what do they see to be enabled by IoT or devices? Where do they want, or where do they see the computations to be executed? Would that be in the cloud? Would that be in edge? And in that time, they projected that in 3 years, which is 2017, so 3 years before now, about 37% of them thought that we could do that on the edge, as opposed to 58% on the cloud. Is that number still true? I don't think so, but certainly, we'd be happy to have a discussion on this and have a counter argument for it. All right. Another interesting thought came in 2015. This was a projection from 2013, and I think this really sums up where we are right now, right? This is the amount of data that is being produced up until now. So the projections were for 2020, and I'm really looking at projections because I want to make sure that we understand the past and the present and where we're going to the future, right? So this is a projection in the past, right? In about 2015, 5 years from then, how would 2020 look like, right? So the interesting part over here, this is the entire internet traffic, the amount of data that's being generated, right? Things that we would kind of imagine that would do a lot of traffic generation would be, images, voice, video, because that's predominantly what we use for it right now, right? With all the social media involvement and so on and so forth. But the surprising element here is that even in that time, the projection there was, yes, in 2011, we only have a 0.1 zettabyte is being produced from Internet of Things. In 2020 will be 11.5 zettabytes of it, right? But the interesting element here, which is not really included in it, is that surveillance data has actually ballooned up from 0.9 to 62, right? Now, you will say like, oh, well, that's pretty much exactly like Internet of Things, right? But no, because the definition that at least I'm subscribing to it is surveillance data would simply be a passive data, right? You're observing some environment. You're not really doing some real-time action on it. But again, there may be some applications where you may want to require some real-time input in it, right? Such as traffic signals, or you have home security systems or premise security systems and so on. But I thought this was very interesting and really spot on, because even, whether you subscribe to this definition or not, if you include it, about 75% of the data is really produced by Internet of Things, right? So where is this data going, right? What are we trying to do with it? I think that's a good question to be asked. Right? So now looking at the present, right? There was all projections, and we all subscribe to it. What is really happening? So the interesting point here in this particular graph, this is by IoT Analytics, is, and this was done in last month, that this year, right, 2020, is the first year in human history when IoT devices are more than non-IoT devices. And they clearly define what is an IoT device versus non-IoT device. So a non-IoT device would be anything that is a mobile phone. So that's not considered an IoT device. Tablets, PCs, laptops, anything that has with fixed network capabilities, right? Phone lines and et cetera, et cetera. So IoT devices here that are being considered are all B2B devices, all consumer devices, stuff that you use at home, stuff that has a very closed loop, really not engaging too much into the backbone network and so on and so forth. So that's very interesting because now you have more devices of these. And the projection in next 5 years is these would be about 3 times more than what we consider as a non-IoT devices, which would be mobile networks and so on. So very, very interesting. To me, that was kind of an eye-opener, right? Of course, if you want to understand how it's cumulating up, the cumulative increase would be roughly 3%. That's a cumulative increase. So that's quite a bit. All right. So now, I was very interested to see, like, okay, where does this IoT really fit? Is it like an edge computing thing? Because really, you are getting all this information from auxiliary devices that should connect to an edge, right? A base station or something. Is it really integrated into cloud? We have to draw some line somewhere, right? And going back to the original definition, you have to have a control loop. So you have to have an actuation somewhere, right? To me, an actuation really resonates with, I have to have a response very, very quickly. Otherwise, we are in trouble, right? So these could be something similar to real-time systems, right? Could be hard real-time system, could be soft real-time system. You want some response back to what you have actually observed, right? And I think that kind of dictates, being dictated in this particular nice illustration by Moore Insights over here, right? If you want the response time to be increased, right, you want the network and analytics latencies to be decreased quite a bit, right? And you want all of these operations to be actually done, most of them, on the sensors or on the edge devices, and nothing being sent back to the core network or in data center, where you can really look at deeply into, what is your data producing? Do you want to do any analysis, deep analysis in it, some learning algorithm, and so on and so forth, right? But more or less, if you want a quick responses, really these would be the prescribed, actions to whatever you observe. Really would be, you have a lookup table, you go into it and figure out what exactly needs to be done, and you take an action, and if it's not, then you just punt it back to, I guess, cloud and figure out what would be the auxiliary action. And you just, hold your arms in the air and say, well, we couldn't do it, and that's because we just don't have any information on it, right? But again, these should view them as decoupled type of processes. There's so much of an item that you can put in a lookup table, right? New items would emerge, and that's where you want to go back to your cloud and get the information back and push it and update your lookup table, right? But if that's the the IoT type of an activity, right, or IoT dictated type of an activity, we're kind of limited to what we should do and what we can do, right? So with that thought, 3 years ago, we published a reference architecture for how an IoT or fog IoT, that's what we call it, just to be differentiating from everybody else. Really, it is an IoT, and how it should look like, right? So we started off with, all these IoTs, right, should be dictated by the application, right? And that's simply because, you cannot design a sensor cheap enough, which would be, equally useful for example, in agriculture or in health informatics or in transportation. They have to be specifically designed for that application, right? So it has to be application driven, right? It must have some correspondence. So within that particular IoT domain, you could use various different types of networking protocols, but at the end, right, you have to have some interface with a radio access network, right, or an RN or CWAN, whatever you prefer. And all of them have to be then kind of be federated one step ahead, and then there would be the edge server. This would be kind of be a little bit more have a little bit more computation than your premise, perhaps, and perhaps could also do some aggregation, right? And the RAN is important here is because you do want to make sure that you capture the mobility aspects of it. All the RAN traffic is different. The circumstances are different. The handoff has to be also enabled as well. And then you kind of go back to, also talk back to the core network, and you have the federated cloud servers there, which kind of can aggregate various different types of IoT clusters, or within a cluster, it can also provide more computational capabilities as well, right? For the RAN, we kind of didn't limit it to, the usual cellular services. It could be cellular, it could be WiMAX, could be WAN, anything of that nature. And I think that was a well-received type of an architecture, kind of simplified all the things. You sense certain activities. Of course, for a quicker response, you have to have actuation right within that particular domain, and that actuation would be different from one domain to the other, right? And for activities that are not present in your immediate action apparatus, that can actually be sent back to the edge server. It can figure it out. That's fine. You can send it back again for action items. If not, then you send it back to the federated cloud server and do more operations on that. So the reference architecture that we provided here essentially had 4 levels, and that really corresponds to what you're actually seeing over there. The hardware layer and the reconfiguration layer would be present on the devices. So different types of network capabilities could be there. You talked about configuration of managers, of the hardware modules, and on top of them, some virtualization layer. So that's easy to use, easy to manage on-premise, and also have a reasonable type of an interface to your edge servers and so on and so forth. The analytics layer, it depends on the application, but more or less what we wanted to do was, because you are analyzing things, right, rather than having a very fast type of response, it resided in the edge server. You can gather different types of statistics with it. Of course, you can dictate a power management methodology for your edge devices, because we're assuming that they will be battery operated and so on and so forth. And of course, you can have some machine learning module on top of it to learn from various different types of IoT clusters that are pushing data back. Right? And at the cloud level, we have the application layer, some virtualization layer, and of course, some interface to the edge server applications that can be independently developed. So that's the architecture that we represented and in 2017. And since then, we have been working on it to enhance it through various different aspects of it. And they're published in various different places, right? Starting off from SSC in 2017 to the recent one in Cloud Summit in 2020 and 20. So I'm not going to go through all of these papers. Of course, you can talk about it offline, but one of them I do want to mention. This was in IEEE TSC in 2019, where we used a double deep Q learning module, right? So again, the problem there was to see if we can, in a federated fashion, do energy management of all the IoT devices, right? And of course, this is an important problem to deal with it. However, these schedulers are highly unstable, and the reason for that is because they are capturing various different types of information, and the information is coming in at various epochs and in various different types of controls. So what we basically did was we produced a Q value for each of the DVS algorithms, and it was a suite of algorithms that we kind of ran with a targeted network to produce the target Q values to be trained for the parameters, and the rectified linear units functions were actually also used as the activation function for the double Q deep learning module. The net result was, yes, you can actually achieve a greater energy efficiency over here. I think what kind of came out of this work was it's very, very difficult on a large scale to actually do any type of federated learning. It's quite challenging to do that. So to address this challenge, we thought of, well, the first way would be, we can also enhance it a little bit further, but from all of our different works that we did, we thought that, well, let's try to make a simulator for the community. This is actually just very recently accepted. It's called XboxSim. Don't ask me why we call it XboxSim. That's because that we couldn't really figure out another name for it. There's a lot of stuff happening in box simulators. And the only thing we could come up with is just, oh, let's just call it XboxSim, and X could be replaced with anything that we think of. So you can actually download it. It's publicly available now from GitHub. Simply it's XboxSim. We'll be able to download it. I think the good thing here is it does provide fog federation for it, does integrate IoT fog and cloud, does capture multiple distributed fog locations, right? So that's the new element we brought here. In terms of the energy efficiency, because we wanted to keep at the reference architecture over here, it has to be at the fog level. And that's pretty much understandable because, these are the devices which will be at the forefront, really not the edge server or cloud for that matter. But it's easily extendable. We encourage you to kind of use this. The other interesting elements would be you can incorporate a lot of mobility models in here. So, the IoT module here is not a static environment. So you can think of, extending it to transportation or in agriculture where things do actually move, right? If you want to know more about, some of the interesting cross-sectional type of activities related to big data and IoT, we do have an edited book which is recently out there. Strongly encourage you to read them. Most of the work is actually from the community, about 10 chapters, talking about various different types of activities in relation to IoT and big data. Right. So that was basically the system angle of all of these things, right? But I think what is really interesting, what research can we actually focus on, really is perhaps not so much of interest to me, at least, is in the systems aspect of it. It's actually in the communications now, right? And what is the interesting element over here, right? So if you look at, the range versus bandwidth, I think that's always the dilemma that we are facing off, right? So near field communication, RFID, of course, is just a meter or so with very low type of bandwidth activity. If you look at the satellite, of course, the range is hundreds of miles, right? But the bandwidth may be kind of limited. If you look at the 5G, of course, the bandwidth is quite high, and the range would be simply be dictated by what type of a base station you have. So the interesting element here, right, which is actually enabling more and more IoT type of devices, really is in the newer communication protocols, right? So such as LoRa, such as Sigfox, and the newer ones from NB-IoT, right? These are low power LAN, so essentially they are enabling devices to be operating on battery for very long range and with reasonable amount of bandwidth, right? Again, dictating back that we need this for actuation more than refinement of knowledge discovery and so on and so forth, right? I think the interesting part here would be when we're talking a little bit detail would be NB-IoT, because you can essentially also embed them into the 5G communication as well. All right, so what is the difference here? Well, they're all different, right? If you look at the LoRa, really using its own uses its own type of gateway, has its own network server and application server, and then on top of that, it's building up different application interfaces and does give it to industrial application or cold chain and so on and so forth. If you look at the other extreme, which would be NB-IoT, I think the difference here would be it doesn't require any of the gateways or an access point, uses the current cell tower, which brings it easily deployable, I guess. And the network there is really the carrier network, right? And on top of it, you can build the APIs and then you can build your own applications of it, right? Which one is better than the other? It's kind of difficult to say because, again, they are in the phase of developing their own ecosystem. So that's one. I think the problem really with the NB-IoT is because you really are dependent on the carrier network, they have to figure out a business plan, right? And I think that does not really exist in my opinion. Perhaps it may be, they'll figure it out very quickly. Others are heavily relying on their ecosystem, and whenever you're doing that, I guess you have to do the heavy lifting, and I'm not sure that would be a fruitful exercise, but perhaps it would be, right? So there was a nice study presented last year in ICT Express, doing a vis-a-vis type of a comparison of, which one do you want to choose, right? So again, they chose the top three, communication platforms here, NB-IoT, LoRa, and Sigfox. And, the key elements as a system researcher, you would always ask, tell me about the range or the deployment cost or the cost effectiveness, the battery life, quality service, and payload. And you will see all of them are actually different, right? And, which one is better than the other, it's very difficult to see. Perhaps you just looking at the graph, you will say like, oh yeah, LoRa and Sigfox are very, very similar. And in fact, they will be very, very similar because, LoRa and Sigfox, they have their own gateways, they directly talk to the cloud, and then on top of that, they have application server, right? So they would be, the range would be quite high, but I guess and then of course the development cost would be quite low, right? So that's why they're cost effectiveness. But in terms of scalability, they will suffer because they're relying on their own ecosystem. In terms of latency performance, they would suffer again because they're relying on their ecosystem. The payload length would also be suffered, right? And then of course with scalability comes quality of service. So you make your own judgment on this, which one you would like prefer to use, but the jury is still out there, right? Lux Research did this analysis of comparing how many people actually use or how many countries are using various different types of technologies. And of course, clearly NB-IoT is the largest over here in terms of company, in terms of the countries. And of course, all the big name telecommunications are actually all over here, right? So China Mobile, Vodafone, AT&T is still there. But it doesn't take away anything from others. Of course, like for LoRa, you have the Swisscom there, Tata is there, Comcast is there, and so on and so on. All right, so I was also interested in, okay, what type of other ecosystems are there, right? So Intel IoT platform, they had a roadmap given about 6-7 years ago, really subscribing to, the definition provided by NIST. Again, it's on the premise, but some of the elements can be done on the cloud with the cloud management, and they have their own gateways and so on and so forth. Where is it going? I'm not so confident it would evolve into something interesting, but just wanted to throw out there that other elements, other companies are also interested in it. Nokia have a little bit of a larger picture on it just because of their cellular devices. So of course, object tracking, video surveillance, and all sorts of activities are actually enabled by Nokia's version of the IoT. I think the most promising one is by ARM. This again is from their own white paper. ARM, by general, we know that they're in the chip manufacturing, so they have a lot of different platforms, that most of us are not really looking at, from mobile implementation all the way up to very highly optimized variable devices. And I think at the end of the day, right, you do want a processor that can actually do a lot of computations at a very, very low cost, a very low energy footprint. I think ARM is certainly one of those companies. Now, the interesting part of that would be they just don't stop over there. They're trying to slowly build up their own ecosystem, which they call it embed, right? So they have their own silicon partners where they're enabling crosstalking. So this is Freescale, and on top of that, there would be other platforms of megachips, multi-tech, and so on and so forth, with the cloud partners, looking at how they can actually interface with them. So they really are pretty big with Telenor and IBM and Salesforce. It remains to be seen after their acquisition, but certainly to me, this was the most promising ecosystem really growing. All right, so this is all about okay, where does the academic individual fit in all these, right? Not everybody would have access to ARM or to Huawei or any other elements out there, right? What can academics actually do? So this year in June, this is a snapshot from Communication Magazine. We talked about this advanced wireless for unmanned aerial system. This is a test bed that is being developed at the North Carolina State University, which is a lead institution, and Mississippi State. And the idea there would be, what if we actually provide with researchers from universities, researchers, right, to do field studies, which would very closely mimic to activities in the field, right? So these would be, we are currently resurrecting the cellular base stations. These would be all aerial vehicles. So this particular test bed is for air vehicles, but to instill in different types of mobility models, looking at different types of applications. Agriculture is pretty big at Mississippi State. So we're using that as an activity here. We will provide a interface to general user, which can log into the portal, and the AirPower portal would enable them to say, well, you do want to do simple simulations, do you want to do real emulations where actually drones are actually flying, and so on and so forth. Provide them with some actionable items in terms of data storage. We'll give them VM images. You can also resurrect some of their sandboxing. All of these activities are actually enabled by radio access networks, so programmable ones are put in place. Eventually, this is a little bit behind the schedule, given all this COVID type of activities, because essentially all of these equipment really are donations from cellular companies and many other companies enabling telecommunications. So eventually what will happen in the next few years' time, strongly encourage you to utilize this when it's up and coming. So this would be one of the 4 test beds that the National Science Foundation actually funded the last few years. Some of them would actually be at Mississippi State. So that's fine, but what really we can do, this is a interface with cellular base stations. Of course, you can consider these USs as small, tiny little devices with IoT type of capabilities. But what else we can actually do? Can we actually interface it with some other test bed that perhaps we can do some edge computing type of computations as well? So what we have also at Mississippi State is the CAV Center, which is the Center for Advanced Vehicle Systems. Currently, we do have about 55 acres of what we call a proving ground for autonomous vehicles. This is funded by various different DoD sources. So what you're seeing on the screen here is actually the snapshot of all these 55 acres, wooded land, really in the natural environments, to test autonomous systems. In this particular case, is the vehicle, because we want to have some distillation of that choice. Essentially, these two test beds or the test fields would be merged with each other, giving a tremendous amount of interface to the research community to test things in the field. Now, the interesting part here would be, because this is natural terrain, with all different seasons, the terrain actually would automatically change. So, your algorithms need to be adapted quite quickly. We are not in secluded type of an environment. So, the natural terrain actually changes with the varied conditions, and you should be operating in pristine environment. All right. So coming back to the data, right? This is all good. Let me show you I think this is very popular to capture what type of data is being produced every minute of the day. And the interesting part over here is all of these, right, actually states what is actually being produced as consumer images, voice, and video data, right? And what we simply ignored was what is being produced by Internet of Things and surveillance video. So this should basically be a very, very alarming type of data plot that actually you see all the time, right? All right. Then I was very interested in, well, it's a lot of data, so who is doing what in terms of the data, big data landscape, right? So bunch of folks, they always produce this landscape type of infograph, which actually tells us what type of companies do what in what domain, right? So from application to analytics to infrastructure to cross infrastructure and analytics and open source projects. And the obvious names that you will see is, oh, okay, Hadoop and HDFS and Cassandra, and could be these Opera and so on and so forth. But a lot of these companies, right, are not very, very known, but it's a huge amount of effort is being put into various different types of applications again, right? So using this analogy of IoT is important for us. The data is important. What we can do with this data, we also have a series of work that looks into a very specific application-driven type of IoT activities, right? So more or less, it's in health informatics. So a series of work we published in 2018 and 19. But the one that I'm going to talk about now was what actually started all of this in 2016 in PMC. So what we did was we analyzed about, altogether about 1.2 million healthcare tweets. We analyzed about 10K provider profiles. They would be doctors, nurses, and working with some predefined topics. So Twitter does allow you to have predefined topics, and health communities. You'll be very surprised that Twitter also has some community built up there. Right? So the idea was, what if we are able to develop a system where you actually provide some of your generic type of symptoms, right? So for example, headache, or you're coughing, or you're sneezing, et cetera, and what if we are able to match you with a certain healthcare provider that you can talk to Twitter on Twitter and get some diagnostic of it, right? You'll be also very surprised that actually, yes, this actually happens, because they know that healthcare is quite expensive, at least in the US. They will talk to these individuals on Twitter and figure out, well, is it real or not, right? If it is real, then you need to definitely go and consult a doctor. If it's not, then perhaps you may take some counter type of stuff, and you'll be all good at this, right? So there are two different systems in this particular work running in parallel. The first one is the declarative filtering disease risk assessment. And now the question would be, well, where do you get this disease risk assessment? There is a database actually available. It's called Enhance. It's from 2009 and 2010 era, where it actually gives you a very close mapping of, given your symptoms, what class of health problems you may actually have, right? So the user may log in, provide some basic type of information, which could be name, age, height, et cetera, blood pressure, and you build this profile of activities, and you have these existing users for basically multiple diseases, which actually is provided by the Enhanced database. And then out of them, you actually retrieve some these specific type of profiles, which is actually matched to the closest match to the user actually requesting that particular activity, right? You do the similarity computations, right? Because a headache with a normal blood pressure may mean something else with a headache with high blood pressure, and with higher weight may dictate something else. So the similarity computations is actually done, and we do the risk assessment score based off it. And then it's basically sent to the other system, which is the Twitter-based health expert recommender. So out of those, we do the tweets retrieval so that you can actually do it by the API that is provided, and you do the bulk analysis because it wouldn't allow you to do direct streaming of it. You store, and then you kind of retrieve what you actually have gathered from that API. The tweets are actually tokenized first because we wanted to make sure that something that is written in natural language is translatable into meaningful type of an activity. So some natural language processing is actually done on that. And then the candidate experts are actually identified. And you will be surprised that sometimes, as they always say, we're all doctors. We try to prescribe different things. You'll be surprised that a lot of users out there and Twitter, they will actually give you information that almost sounds like, yes, unless you analyze them for quite a bit of a time and figure out, who's the candidate and who's not, it will be very difficult for a novice user to actually see that this is actually not a doctor and just pretending to be one. So once that is done, we do the disease-specific segregation through the HITS Hubs and Authority protocol, which is quite common over there. And this is all done in parallel and periodic. So the lesson learned here is, and then of course you rank the experts and give it back to the user, and it's up to the user if they want to interface with one of them through tweets or not, or simply go to the doc. The lesson learned over here is, it's quite, doing, unless the application is very, very straightforward and you know all the parameters of it, right? It's quite difficult to comprehend various informations coming in from various sources, right? The typical big data problem, if you want to really do it in the field, right? And this is the system that we actually developed. It's actually deployable if somebody wanted to do that, right? It took us 2 years to get it done into some meaningful aspects of it, right? So that's the lesson learned. Kind of hard lesson for us, but certainly encourage everybody to pursue this in the future. Right. So for the last side of the coin, I was also very interested in, who is doing AI, right? And where are they getting this data from, and what type of platform they're using? And also, CB Insights regularly updates this AI 100 table, right, which basically lists all the top 100 companies that are, in their opinion, would be the would do the breakthrough. And if you look at all of them, right, you'll be very surprised that the usual names, right, such as Google and et cetera, do not show up, right? These would be the emerging trends, something of undercurrent that is happening. And they're very, very specific to the domain. So healthcare is an example that we took, and the companies that would kind of emerge out would be, Babyline or Deep Genomics and Genomic AI. If you look at the IoT on industrial IoT, right? Sight Machine is one of the names, and Connix is, of course, I know Connix, but most of the folks may not know that as well. Interesting activities are happening in fintech, and of course in automobile as well. So to bring everything together, right? This is how I approach my research, at least when we're looking at IoT and when we're looking at big data and then AI, right? So step one is to first understand the domain, right? I want to know everything about the problem that I'm solving, right? If I don't know, perhaps I'm just applying some generic type of an activities. The literature is actually full of it. But I wanted to know, and that's the step number one. So I have to interface with a domain-specific person, right? The step two, again, would be, yes, we want to build a kind of a four-step process over here, which talks about, also has interface to the hardware, but it has virtualization layer in it. It has analytics layer in it. It has the final server layer in it, the application layer in it, right? Which would be very specific to a domain, right? And the third step would be, yes, I'm getting data out of this, right? What do I do with it, right? So I can certainly use data analytics for it. This would be the big data type of a component. What data is useful at what time, can I draw some correlations of it, and then apply AI to really close the loop, right? And these are the four steps. Now, for an application to application, yes, the step four may be in parallel to step number two, or it could be after step number three. But essentially, that's a point of view that I take when I tackle any problems in IoT or big data or assisted with AI as well, right? So some examples that I can give you. This again is also a series of work. This is of very practical relevance over here. You're looking at, of course, at my older institution at Fargo. We were prone for spring floods because the river that would flow in the middle of the city was actually the higher elevation than the city. So rapid snow melt would actually trigger floods. And so the idea there was, right, can we develop some sensor modules that you can embed into the roads and interface with roadside units? And can we figure out a way that we can have a timely and precise type of evacuation rather than having a mass evacuation, right, which actually triggers a lot of other psychological and sociological problems over there, right? So we did develop the sensor module, and actually I have it in my office. I can show it to you after the presentation. We did develop the roadside unit and try to embark on this study of how we can actually do it. It is of a practical relevance, so it took us quite a bit of a time to gather all the data, the right road conditions, the right road safety, the right shelter place. And then you also have to interface with the city planners because they have the city evacuation plan, and if you want to do a vis-a-vis type of a comparison, like what is better, is it your system better than the actual one that is actually approved for evacuation, you have to have a good interface with them as well. So anyway, the idea there is you gather data from the sensors embedded in the pavement, you talk to the roadside units, and then you bring it back to the cloud server and do analysis and do it at a quicker rate of time, so that you can redirect the evacuation as you progress forward and send it back to the roadside unit where it can actually dictate the evacuation. Anyway, so we have a lot of results. They're all graphs, right? Is it better? Yes. I mean, we show that everything. our process was better than anything else, but that's really not the conclusion that we want to distill it out of you, right? Really what highlights this impact is if you really want to do things in practice, right, the amount of data, right, and how you parse the data and how you actually make interface to the data really dictates, right, your performance, right? And it's a very, very tedious type of a job, right? So for example, if we double the size of the regions of recommendation, right, in terms of the iteration time, iteration time actually is increased by 26%. That's quite large given you have a catastrophic event happening, right? If you double the size of the map that is you actually being processing, right? Your average time actually increased by 76%. So interesting results came out, again highlighting the aspect that it's quite difficult, and if you want to do things in practice, right? So finally, who do I think would be the forerunners here? It has to be done at a scale, and it has to be done with an application that resonates with the folks on the ground. Singapore has a project called Smart Singapore. You can let go of your wedding ring and put this on, save your life when you're a little bit aged. It can detect falls, it can detect your health. It can also detect where you are, can inform people at various locations and law enforcement agencies when you come along. Of course, India has embarked on Digital India. I think that would be a fantastic project, and I'm looking forward to what they will enable. Of course, the most interesting one is being unfolded in Dubai, which is called the Smart City Experience. Pretty much all of their activities, right, and especially the ones in e-government, are being pushed into being one-stop shop type of an activity, right? So we're all already experiencing the future of transportation over there, including the air taxis, smart parking, which I really would like to have, not in Starkville, it's a small city, but at least in DC area. Again, as I said, one-stop shop for all government-related activities. You just kind of go there and just interact with the kiosk. But what really is interesting is it is now the IoT enabled with big data, easy of applications, easy deployment, right? It's enabling community involvement, what I call the citizen science and engineering, right? The project out there is called communityfridge.org. Have a look at it, download the app if you're in Dubai. Would actually tell you in Ramadan, right? This is our holy month of fasting, what restaurants you can actually go which will give food for free, right? Because these are the leftover foods, and they don't want it to go to waste. They would rather give it away to folks who observe Ramadan. Fantastic. Only a person who actually had no knowledge of computer science or computer engineering actually developed this app because he felt the need of it, right? And I think it's the exciting point in everything that is going to be enabled to IoT. Now, the critical element here would be, well, that's a lot of data. Can we, we don't really talk to each other. These different organizations are very skeptical about it. Last week, right, in Dubai, they launched this Nabi project, which currently, if you are a patient in Dubai, you can go to any health provider and not worry about, really starting from scratch about your health history. The health history will actually just kind of go with you. It will be readily interfaceable. So currently about 1 million people have this capability, and after all said and done, in the next year or so, about 10 million would benefit from it. So if they can do it, certainly we can do it as well. But these would be the exciting places to look forward to in terms of IoT, big data, and AI related activities. So in the end, I thank everybody. This is just my point of view, not the point of view. So I'll be happy to take any questions if there are.
That's great. Thank you. Thank you so much, Sami. That was a very interesting tour of different kinds of technologies out there. So I'm just waiting for any questions from the, let's see if there are any questions here. So there's one question from Anthony Miller. So thank you for your talk. It was very informative. Can you please tell me your thoughts on IoT, big data, and AI when quantum computing becomes commercially available? As quantum supremacy has been achieved, so it's a question of when RSA encryption has been compromised and when quantum completely supersedes classical computers. Hmm.
Right. Yeah. That's the tough question, right? Um, so. Okay, when it will be achieved? Yeah, I don't know when it will be achieved, right? So the claim of quantum supremacy is also, it's kind of relative to everybody's claim. I will just say this: the jury is still out there. I think what was promising was quantum communication, but after I've read a lot about it, I'm not so sure about if that is actually happening. But anyway, coming back to the question, it would be a very, very exciting time for us, right? All of the what it would do for AI, what it would do for data analytics would be to just push it to the next level of greatness, right? But there's a lot of work that needs to be done, right? So the classical algorithms are not ready to be portable, right? That's there. There is not an easy way to interface with quantum computers. That's another. The cost is going to be prohibitively large, right? So right now, where we are, for example, if you want to map it to the classical computer history, we're in 1960s, right? Where the mainframes were just starting to unroll, right? So hopefully it would not take another 50 years, but more or less it would take a decade or two to bring it into layman's hands. But everybody is also cautious of the fact that perhaps encryption would be broken. So there's a lot of funds that are being funneled. Just I guess that's not one aspect of it, but one of the main aspects would be to tackle that, right? So at least from the U.S. side, I can tell you that last year, that just inaugurated this year, funding was there for last year. About $100 million were actually spent into creating 4 centers of excellence in quantum. That's not a lot of money, but still a certain starting point. But more is to come. Right? So I do realize that I'm not answering the question directly. I am excited about the opportunity. How would it unfold? But to me, it's quite a steep learning to port things that we are currently doing very, very efficiently into the quantum world. But eventually that will happen.
That's great. Thank you so much, Sami. So I have a question from Ashik. Ashik, do you want to unmute your microphone and just ask directly?
Yeah, so by the way, Sami, this was very, very good talk. Thanks for your time. We enjoyed it. So thanks for the insights. My question is, most of the IoT devices are mobile phones or actuators, whatever we have on the edge side. We know they are very reliable. We could trust them, not from the security perspective, but from more reliability perspective. However, AI is still in its early stages, and reliability and trustworthiness is missing. What do you think? So when we would be able to achieve the same level of reliability and trustworthiness that we have basically, or we get from devices? What's your
right?
opinion?
I think Ashik, the answer would be when we are 100% sure that the devices are reliable, then our algorithms would be reliable too. I think the bigger question to answer here in the AI field, right, would be, and that would automatically answer the trustworthiness of the AI algorithms would be: are we 100% sure that our AI system is cognizant, right? So cognizant would mean that you're absolutely certain that you have arrived at a state in your final state machine, which you can actually describe, right? And I think that would really enable trustworthiness. That would also enable reliability. I think on the broader perspective, of course, The other element that would assist in is if we are able to embrace as researchers reproducibility of results, right? I think that's a problem that we are facing right now, right? That the graphs looks great in the papers, but are you able to reproduce it, right? Perhaps not. And I think you'll say like, oh, what has that got to do with the AI and trustworthiness, right? Because that's the first step, right? If somebody else is able to verify, your biased or unbiased AI algorithm, right, we would be in a position to quantify ourselves, is it trustworthy or not, right? So I think it has to be done from many different angles, and many different folks have to chip in.
Okay, great. Thank you. Thank you, Sami. So I have one more question. So great talk in your explanation of IoT. Are you considering actuation from the point of the actions taken at the data source, or does this cover actions taken remotely too? What level of real-time responsiveness is being considered?
Right. So it's mostly at the data source level, right, on the sensor level.
Okay,
right?
Great. Perfect.
So that's there. But in certain cases, for example, in the example that I gave for the evacuation, right, that responsiveness has to come from the cloud level. We have to analyze at a level that gives you the overview of the entire evacuation, and then send back the responsiveness. But you have to consider that in that particular instance, right, the real time is a little bit of slack, right? The cars do not move, for example, in evacuation at a very fast rate, as opposed to, if there's a burglary going on or a bank is being robbed. I mean, of course, that case, the response has to be absolutely quick and certain.
Okay, great. So I just have one last question. That's from me, Sami, if you don't mind. So Sami, I think you have a very unique perspective because you work for NSF and you've also been at academia, for many years. So I was just wondering, in terms of the coverage that you showed in your talk, IoT is such a big thing for industry right now. There's such a large number of players that are working in this space. So where do you see the niche for academia in this area? Because, the question is, right, by the time that we've done something, the industry might have already stepped, 10 steps ahead of us. So where do you see the kind of, I guess, the sweet spot between what academia can do in order to complement what industry is doing from the various perspectives you have?
Right. So I think the good question. Never mind questions from you. I think the differential here would be the industry is at this particular instance of time, right, is really focused on the industrial IoT, which would be these factory type of environments. Again, looking back into, this is a cyber physical systems, real-time responsiveness, kind of go into the Sigma type of environment, right? How we can improve the performance of an industry to the level that is meaningful, right? Where the academics can put in their or carve their niche here is really the scale of this IoT, right? That the industry cannot really handle at this particular instance of time, right? So what is the scale? So scale is beyond a premise, right? Can it scale across different domains, right? Can you actually do it at a city level, right? That an industry would simply be not interested in because it's not in their fiduciary interest, right? Why would they benefit, a city, right? A city has its civic duty, right? And that's, I think, what academics can actually pitch in. So where are the interesting points here? Again, interesting communication modules, right? Low cost, long operational type of device development, right? Really trimming down the OS to the level that does provide a lot of interface to the hardware, but it also is leaner as compared to the other activities. Also in sensor development, there could be a huge leeway that can actually be made. What I always tell folks is we do a very good job in observing things around us, right? But we do a horrible job in observing ourselves, right? So that does not mean just putting cameras on ourselves, but our body, how does our body react to different day-to-day activities? Can we learn a little bit more about us, right? Can we do precision medicine, right? And I think that activity, right, is not on the horizon of the industry, and I think that's where our academics individuals can really make a difference.
For that, thank you so much, Sami. That was a really very interesting coverage, and thank you for your time. Really appreciate it. So maybe we should just do a virtual. Thank you very much. Thank you.
Thanks so much for